Around 300 million years ago, Earth had only one giant supercontinent called Pangea, which was bordered by a single ocean called Panthalassa. The explanation for Pangea's origin gave rise to the contemporary theory of plate tectonics, which holds that the Earth's outer shell is broken up into many plates that move across the mantle, the rocky shell under the Earth's crust. Several supercontinents have developed and broken apart during the planet's 4.5 billion year history as a result of churning and circulation in the Earth's mantle, which accounts for 84% of the planet's volume, according to the US Geological Survey. The breakup and formation of supercontinents has drastically impacted the history of the planet. Pangea's history. After assembling multiple lines of evidence, Alfred Wegener suggested the concept of an ancient supercontinent, which he dubbed Pangea, more than a century ago. The first and most evident was that the continents fit together like a tongue and groove, which was easily seen on any precise map, according to Murphy. The geological record provides one further indication that Earth's continents were once one single mass. Pennsylvania coal deposits are comparable in composition to coal deposits from the same historical period found in Poland, the United Kingdom, and Germany. This implies that North America and Europe were originally a unified continent. According to the online etymology dictionary, the term Pangea is derived from the Greek words pan, which means all, and Gaia, or Earth. The supercontinent evolved gradually over hundreds of millions of years. According to a chapter in the scientific book, Ancient Supercontinents and the Paleogeography of Earth, almost all of the continents were in the southern hemisphere during the early Phanerozoic Eon, 541 million years ago to now, with Gondwana the largest, spanning from the South Pole to the equator. The Panthallassic Ocean dominated the northern hemisphere. Another ocean between the paleocontinents, Laurentia, Baltica, and Gondwana, began to close during the Ordovician period, 485 million to 444 million years ago, and then disappeared during the Silurian period, 444 million to 419 million years ago, when Baltica and Avalonia collided with Laurentia to form Laurasia. Finally, some 320 million years ago, Gondwana, Laurasia, and intervening terrains combined to form the Pangea supercontinent, according to the chapter, written by Earth scientists Trond Torsvik, Matthew Domeyer, and Robin Cox. However, Pangea was not the megalith that most people believe it to be. According to the chapter, Pangea never contained all of the continents at the same time. For example, during the Carboniferous 359 million to 299 million years ago, the Paleo-Tethys Ocean to the east of Pangea remained vast and served as a barrier between the supercontinent and a number of huge separate Asian terrains, including Tarim, North China, South China, and Anamia. According to the chapter, during the Permian epoch, 299 million to 251 million years ago, many old peri-Gondwanan terrains slid off the northeast Gondwana margin, kicking off the opening of the Neo-Tethys Ocean. When did Pangea break apart? Between 195 million and 170 million years ago, Pangea split up in many periods. According to the chapter, the separation began some 195 million years ago in the early Jurassic era, when the Central Atlantic Ocean opened. The supercontinent mostly fragmented along prior sutures. According to a 1970 publication in the Journal of Geophysical Research, India separated from Antarctica, while Africa and South America rifted. North America diverged from Eurasia some 60 million years ago. Pangea's climate. Having one enormous continent resulted in dramatically diverse climate cycles. For example, the heart of the continent might have been completely dry due to gigantic mountain ranges that prevented all moisture or rainfall, according to Murphy. According to a 2016 paper published in the journal Paleogeography, Paleoclimatology, and Paleoecology, climate simulations show that the continental interior of Pangea was severely seasonal. The researchers utilized biological and physical data from the Moradi Formation in northern Niger, a location of stratified paleosols, fossil soils, to reconstruct the ecology and climate during the time when Pangea existed. The climate was similar to the modern-day African Namib Desert and the Lake Eyre Basin in Australia, with brief, repeating rainy episodes that occasionally contained devastating flash floods. The climate also had an impact on where animals resided. Reptile-like animals in the family Procolophonids existed in one location during the late Triassic, while mammal cousins known as cynodonts lived in another, according to a 2011 research published in the journal Proceedings of the National Academy of Sciences. Cynodonts lived in Pangea's tropical region, where monsoon-like rains occurred twice a year. Procolophonids lived in temperate locations where it rained just once a year. According to the researchers, the cynodonts needed a water-rich environment, which limited their migration across Pangea. Pangea animals. Pangea lived for more than 100 million years, and numerous animal groups thrived throughout that period. Insects like beetles and dragonflies thrived throughout the Permian epoch, as did mammals' forefathers, the synapsids. However, Pangea's existence coincided with the worst mass extinction catastrophe in history, the Permian-Triassic (PTR) extinction event. According to the Geological Society of America, the Great Dying happened roughly 252 million years ago and caused the extinction of 96% of all marine species and 70% of terrestrial species. Archosaurs, a group of creatures that gave rise to crocodiles, birds, and a multitude of reptiles, including pterosaurs, emerged during the early Triassic epoch. And at 230 million years ago, some of the first dinosaurs appeared on Pangea, including theropods, which were predominantly carnivorous dinosaurs with air-filled bones and feathers akin to birds. Current research on Pangea. Scientists have developed mathematical three-dimensional models to better understand the principles underlying continental displacement. Earth scientists Masaki Yoshida and M. Santosh discussed how they developed models of large-scale continental movements since the split of Pangea around 200 million years ago in a 2018 study published in the journal Geoscience Frontiers. The models depict how tectonic plate motion and mantle convection forces interacted to separate and move massive land masses. Pangea's massive bulk, for example, insulated the mantle underneath, creating mantle flows that initiated the supercontinent's early split. The radioactive decay of the upper mantle also increased the temperature, creating upward mantle flows that separated the Indian subcontinent and began its northern journey. So that's the end of the video. Make sure to like the video, subscribe to our YouTube channel, and press the notification bell so you never miss out on our next videos. Until the next video, take care.